Hey everyone, just want to start off and say happy holidays, happy Thanksgiving. I hope everybody is having a great holiday today. All right. Want to jump into a new lesson today. You guys can ask questions as you go through. All right. This is going to be a good one. All right. Homework has been updated, so you guys can go online. You can take a look at your homework, get that done. All right. And then everybody should be good. We're going to be starting chapter 8 soon, finishing up chapter 7 today. All right, let's get it. All right. So the first thing I'm going to talk about today now is called sampling distributions. So a population can be thought of as a complete set of measurements or counts, either existing or conceptual. A sample of a subset of measurements from the population. So when we compute a descriptive measure, such as an average, it makes a difference whether it was computed from a population or from a sample. All right, so let's talk a little bit more about it. So a statistic is a numerical descriptive measure of a sample. A parameter is a numerical descriptive measure of a population. All right. So statistics come from samples, parameters come from populations. Okay. It's important to notice that for a given population, a specified parameter is a fixed quantity. On the other hand, the value of a statistic might vary depending on which sample has been selected. All right. Let's continue. All right, just want to give you guys an example real quick. All right. So some commonly used statistics and corresponding parameters would be, for example, when we have our mean, right? We have two means. We have X bar, which is our sample mean, and we have mu, which is our population mean, right? So populations are parameters, right? Samples are statistics. For variance, right? We have S squared, right, for our sample variance, and sigma squared, right, for our population variance, right? For standard deviation, we have just plain S, right, for our sample standard deviation, and we have sigma for our population standard deviation, right? Also, we're not going to get much into this, but I'm going to mention it. Proportions, right? These are the probabilities of success for a binomial trial, right? We have p hat, which is our sample proportion, and we have rho, which is our parameter, right? Our population proportion. Okay, let's keep going. All right. Excuse me. All right. So often we do not have access to all the measurements of an entire population because of constraints on time, money, or effort. So we must use measurements from a sample instead, right? In such cases, we will use a statistic such as X bar, so X bar is our sample mean, S is our sample standard deviation, or p hat, right, which is our probability of success, right, for example, to make inferences about a corresponding population parameter, such as our population mean or population standard deviation or our population probability of success rho. The principal types of inferences we will make are the following. So here goes the types of inferences that we have. We have one, estimation. Okay. In this type of inference, we estimate the value of a population parameter, aka chapter 8. We have testing. In this type of inference, we formulate a decision about the value of a population parameter, right? So that helps us to make our decisions, right? AKA chapter 9. And a third type of inference is regression. In this type of inference, we make predictions or forecasts about the value of a statistical variable. Now, I scratched this out because this is in chapter 11. We're actually not going to have enough time to get into that. But if you want, after class, right? Like after you guys take the final, you guys can come back and ask about it and we could talk about it. Okay? So to evaluate the reliability of our inferences, we will need to know the probability distribution for the statistic we're using. Such a probability distribution is called a sampling distribution, right? Right. So perhaps chapter 9 will clarify this discussion. A sampling distribution is a probability distribution of a sample statistic based on all possible simple random samples of the same size from the same population. All right, let's talk a little bit more about that. All right, I want to give y'all a little example real quick. Now, normally I like to write out my examples, but this is going to be a little bit long for me. So we're going to have to go with some images. Okay. So bear with me 1 second, please, everybody. All right, just bear with me 1 second. All right, just one little second. One little second. Just make sure. Okay, we're good. All right. See, that's a lot for me to write out, so that's why I want to just put it like that. Okay. So let's do an example for sampling distribution. So sampling distribution for a sample mean. I believe that's Pinedale, or it might be Pindale. Somebody correct me when you guys get a chance. I think it's Pinedale. Wisconsin is a rural community with a children's fishing pond. That's real nice. Posted rules state that all fish under 6 inches must be returned to the pond. Right? So only children, excuse me, under 12 years old may fish, and a limit of 5 fish may be kept per day. Susan is a college student who was hired by the community last summer to make sure the rules were obeyed and to see that the children were safe from accidents. All right. The pond contains only rainbow trout and has been well stocked for many years. Right. Each child has no difficulty catching his or her limit of 5 trout. All right, because apparently all these children are master fishing, right? So let's just jump into the lesson real quick. All right. So as a project for her biometrics class, what's up, man? Right? Susan kept a record of the lengths to the nearest inch of all trout caught last summer. Hundreds of children visited the pond and caught their limit of 5 trout. So Susan has a lot of data, right? So to make the table, right, which you just have down here, Susan selected 100 children at random and listed the lengths of each of the 5 trout that they caught by a child in the sample. Then for each child, she listed the mean lengths of the 5 trout that children caught. So let's take a look. All right. So let's run through this real quick, right? So child one, I'm just gonna say that that's for sample one, right? Caught these 5 fish right here, right? One fish was 11 inches, 10 inches, 10 inches, 12 inches, 11 inches. Then You took those five numbers and we did an average of it, right? Add them up, divide by five, boom, we have the sample mean, right? Now we did this for 100 students, right? Or children, excuse me, 100 children, right? You guys get the idea. Here's 72 of them, but long story short, there's 100, right? Same thing, right? Each one they catch five trout, they measure how long the trout is, then they do a sample mean of the five that they all caught, right? Now let's turn our attention from the following question. What is the average mean length of the trout taken from the, I believe it's Pinedale, Children's Pond last summer? All right, let's look at that. All right. As I said, it's a bit much to write out, so I'm just gonna kind of jump into it. Mhm. I'm sorry? I didn't finish grading it yet, but I will get it back to you next week, Tuesday. Yeah. I was a little ambitious yesterday. I thought I could get it all done last night, but wasn't possible. Yeah. I thought I could, but I just couldn't. No problem. Nice. Oh, Colson, nice, nice. Is that the the nursing research thing? Okay, okay. That's today. I thought that was like next week or something. Yeah. Yeah. Forwarded to you. Okay, okay. I could have swore that they had. I know. Okay, okay. Got you. Okay, okay. Because there's supposed to be some type of nursing research thing where they have somebody big coming here, like a PhD nurse or something, and they're gonna do a presentation. But I think it's in December. I might be wrong. I might be wrong. Yeah. Yeah. But all right, let's look into this, right? So solution, right? We can get an idea of the average length by looking at the far right columns of the table, right? But just looking at 100 of the X bar values doesn't tell us much. Let's organize our X bar values into a frequency table, right? So remember we did that before? So we use a class width of 0.38 to make the table. So here's the table that we got here, right? So we have one, two, three, four, nine classes, right? Our smallest mean we have is 8.39, right? And then we have our class width of 0.38, right? So that's how we're going to each next class, right? And then we're gonna subtract one from each one to get the upper limits. Bam, bam, bam. We have our frequency numbers. Remember, the frequency is the count of how many means fell in between this range right here, right? And then we have our relative frequency, right? Which is you take each frequency, you divide it by the total of everything, and that's how you get the relative frequency. Okay, good stuff, good stuff, good stuff. Nice little blast from the past. All right. No, I'm not going to ask you guys to do that for homework, right? Just trying to build the idea so that you guys can understand what's going on. Okay. All right. So note the techniques of section 2.1 dictate a class width of 0.4. However, this choice results in the 10th class being beyond the data. Consequently, we shortened the class width slightly and also started that the first class with a value slightly smaller than the smallest data value. The far right column of table 7.9 contains relative frequencies, right? The frequency divided by 100. Recall that the relative frequency may be thought of as probabilities, right? So we effectively have a probability distribution because X bar represents the mean length of a trout based on the samples of 5 trout caught by each child. So we estimate the probability of the sample mean X bar falling into each class by using the relative frequencies, right? So this figure, right, 729, oops, is a relative frequency or probability distribution of the X bar values. I'm sorry, this says histogram, right? So the bars of the figure represent the estimated probabilities of the X bar values based on the data in the table. The bell-shaped curve represents a theoretical probability distribution that would be obtained if the number of children, i.e. the number of X bar values, were much larger. So let me show you guys that real quick. Because I'm talking about it, but I'm not showing you the picture. How rude of me. 1 second. I'm not gonna lie, this picture is a lot more beautiful than I could have drawn myself. But here we go. This is what it is, right? We have our frequency, relative frequency, excuse me, histogram right here, right? You all remember how we get the bars. This is our class boundaries on the bottom, relative frequency up here, and make the bars. This red line over here, right? This is the bell-shaped curve, right? That's representing the theoretical probability distribution, right? Again, if the number of children were much larger, right? If we, instead of having 100 children, we had like 1,000, for example, right? So this figure, 7.9, represents a probability sampling distribution for the sample mean X bar of trout lengths based on random samples of size 5. So we see that the distribution is mound-shaped and even somewhat bell-shaped, right? Irregularities are due to the small number of samples used, only 100 sample means, right? And the rather small sample size, 5 trout per child. These irregularities would become less obvious and even disappear if the sample of children became much larger. If we use a larger number of classes in figure 729, and if the number of trout in each sample became larger, in fact, the curve would eventually become a perfect bell-shaped curve. We will discuss this property at some length in the next section, which introduces the central limit theorem. All right. So, a little bit of a side note, right? I was listening to a I can't remember if it was a podcast. Let's say it was a video, right? It was a video, right? Where I heard in the government they actually want to get rid of the penny. I don't know if you guys heard that, right? But they actually want to stop printing the penny, right? So there was an argument that what they would do if they stop using the penny. Let's say you go to the supermarket, for example. This is what they were talking about in the video, was that you would round off your transactions at the end, you know? Say you have like say your transaction came out to 25 cents. 25 is a really bad example. Let's say 26 cents, right? You would simply just round up to the nearest tenth. So then your transaction would be however many dollars and 30 cents, right? Also, vice versa is true too. Let's say after your transactions have gone through, boom, boom, boom. Let's say that you're at 24 cents. So then your transaction would round down to 20, and then you would just pay the tenths, right? Whatever's left over. Right. So at first, when you look at a small sample of people going to the supermarket, let's say 100 people, like this example, right? You could make an argument that, oh, the supermarket is making more money off of the customers and vice versa, right? But if you actually increase the number of people that are going to this supermarket, over time, you will see that it would actually all disappear. It's like everybody would quote unquote break even in the long run. That's a similar idea to what we're discussing right here. I just wanted to talk about that a little bit. All right. So there are other sampling distributions besides the X bar distribution, right? So in the next section, it shows a sample distribution for p hat. In the chapters ahead, we will see that other statistics have different sampling distributions. However, the X bar sampling distribution is very important, right? Sample mean, I mean, right? It will serve us well in our inferential work in chapters 8 through 10 on estimating and testing, all right? Good stuff, good stuff, good stuff. All right, let's talk about it a little bit. Let's talk about it a little bit. Kind of do a little bit of a summary here, right? Just a little bit of a summary. Right? So what does a sampling distribution actually tell us, right? So a sampling distribution gives information regarding sample statistics such as X bar or P hat. The sampling distribution is based on values of the sample statistics from all samples of a specified size n. Right? Let me just turn my volume up real quick. All right. Sampling distributions are used to obtain information about corresponding population parameters. In the next sections and chapters, we will see how to obtain information about the value of the parameter mu from the sampling distribution of X bar. We will also study sampling distributions of p hat, the sample probability of success in a binomial trial. Awesome. All right. So now I want to get into the good stuff. All right. Let's get to the good stuff now. All right. This is called the central limit theorem. All right. This is going to help us out. By the way, homework for this section has already been posted. You guys might have looked at it already. That's fine. All right. Just going over it. So the central limit theorem. So the X bar distribution given X is normal. So in section 7.4, we began a study of the distribution of X bar values where X bar was the sample mean length of trout caught by children at the, I believe it's Pinedale, Children's Fishing Pond. Let's consider this example again in the light of a very important theorem of mathematical statistics. So here we go, theorem 7.1. For a normal probability distribution, let X be a random variable with a normal distribution whose mean is mu and whose standard deviation is sigma. Let X bar be the sample mean corresponding to random samples of size n taken from the X distribution. Then the following are true. The X bar distribution is a normal distribution. The mean of the X bar distribution is mu, and the standard deviation of the X bar distribution is the standard deviation sigma divided by the square root of n. Oh, goody. Let's get into this. Yeah, this is some good stuff right here. Good stuff right here. All right. I love the theory for this, but I have to admit, though, the work for it, little bit disappointing, right? This is some easy work that this is all summing up out to be. We're gonna get into that right now. All right. So we conclude from the theorem, right? Theorem 7.1, here it is, right? We conclude from the theorem 7.1 that when X has a normal distribution, the X bar distribution will be normal for any sample size n. Furthermore, we can convert the X bar distribution to the standard normal Z distribution using the following formulas. Oh, this is the magic right here. This is the magic right here, right? So the mean for the X bar distribution is the same thing as mu. the standard deviation, excuse me, for the X bar distribution is equal to the standard deviation divided by the square root of n. Let's put it all together, right? So you remember our old Z formula was just Z equals X minus mu over sigma. Now we have Z equals X bar, sample mean, minus the mean for the sampling distribution divided by the standard deviation for the sample distribution. Or very simply, it's X bar minus mu over sigma over the square root of n, right? This is on your formula sheet, all right? Let me show you guys where real quick. Just bear with me 1 second. Where are you? Scooby Dooby Doo, where are you? All right, here we go. So we go to chapter 7 right here, right? Right here where it says standard score for X bar. Here goes the formula. This is the one I'm talking about. So Z is equal to X bar minus mu over sigma over the square root of n. All right, let's get back into it. Mhm.
Frequency thing like the CV.
It's similar. It's related. It's related. Yeah. But for this one, what's happening is I'm still doing like continuous distributions, but now instead of me having a single X value, I have a whole bunch of sample means. And I want to use that to figure out my probability, right? So let's go over this, right? So I have X bar minus mu over sigma over the square root of n. N is our sample size, right? But we know that from the top of the page, right? Mu is the mean of the X distribution, and sigma is the standard deviation of the X distribution, right? Theorem 7.1 is a wonderful theorem. It states that the X distribution will be normal provided that the X distribution is normal. So the sample size n could be 2, 3, 4. It could be any fixed sample size we wish. Furthermore, the mean of the X bar distribution is mu, same as for the X distribution, but the standard deviation is sigma divided by the square root of n, which is, of course, smaller than the original sigma, right? So this next example is going to illustrate it. So check this out. Check this out. This is going to be good. This is going to be good right here, right? I'm gonna give y'all an example. All right. So here we go. So probability regarding X and X bar, right? Suppose a team of biologists has been studying I believe it's Pinedale, children's fishing pond, right? Let X represent the length of a single trout taken at random from the pond. This group of biologists has determined that X has a normal distribution with mean mu is equal to 10.2. Hold on. Hold on 1 second. Let me get my Come on, man. I hate when it's let me listen to me. Give me 1 second. All right, this is good. Has a mean mu of 10.2 inches, right? And a standard deviation sigma is equal to 1.4 inches. Cool. What is the probability that a single trout taken at random from the pond is between 8 and 12 inches long, right? So let's be clear. Here's what they're asking me, right? They want to know what's the probability of 8 less than x less than 12. That's what they're asking me, right? And very simply, we know what to do after this. Just plug in the formula, right? So this is going to become probability, right, of x minus mu over sigma less than z less than x minus mu over sigma. Now, let's recap. Where did I get that formula from? Because it looks like I just made it up, right? I didn't make it up. I copied it right from the formula sheet, right? Y'all know I'm on the computer, so I could look at things while I'm like writing things, right? So here we go. You see right here where it says standard score, right? That's the formula that we just used. X minus mu over sigma. All right, let's get back to it. Right after that, all I want you to do is just plug in the numbers. Real nice and simple, nothing crazy here, right? So next, this is going to become what? Probability of 8 minus mu. I forgot what mu was, 10.2. So 8 minus mu over sigma, which I believe is 1.4. Let me check. Yep, it is 1.4. Less than z. Less than, over here, we're going to have 12 minus the 10.2 all over the 1.4. A little bit of math, boom, boom, boom. Let's see what we get. I'm going to do it in the calculator real quick. All right. You guys good with typing this in the calculator, or y'all want to see? Like I could do it on the calculator if you want to see it. Or you want to see it? All right. Let's do it. Which calculator you have again? I forgot. 50. Which one is that? Yeah. Not the 36X Pro, the little black one.
I got what you select up.
Oh, I see. I remember. I remember now. I remember now. All right. So I'm gonna show you how to do this real quick. Let me just get my calculator out. Just bear with me 1 second. I'm gonna use this one right here. And then which one is, I think it's this one. Yeah, just bear with me 1 second.
You have to the 30X.
30X Pro? Oh, that's a good one. That's a good one. All right. What about you? Which calculator you have, man? Yeah, huh? You don't, it's sorry you don't have it now, but which one do you have though? 36X Pro, the little black one?
Yeah.
I got you. All right, all right. So this is not quite the 36X Pro, but it's kind of looks like it, right? So I'm gonna show y'all how I would do this on the calculator. 1 second. Okay. So first thing you want to do, of course, you want to clear it, right? So there's a fraction button on the calculator, right? For you guys, it's actually right above the number 7, right? It looks like this. Let me draw it out. Oh, shoot. Hold on. This always happens. So it looks like this. It looks like a square, another square. I call it a fraction button, right? For me, that's what this N over D is. Boom.
Yeah.
And then when you press it, that happens right there, right? So after that, just type in what you have in the question, right? Each one, no parentheses needed. You need the parentheses if your calculator doesn't have the fraction button. That's when you use the parentheses, right? So for us, this is going to be what? This is going to be 8 minus the 10.2, and then we're going to go down, use a down arrow. We're going to go down, and then we're going to hit the 1.4, right? And then you just want to hit enter, and it's going to give you an answer, right? For our formula sheet, we want to round that off to 2 decimal places, right? So, hold on, let me come back over here. So this is going to become what? Probability of -1.57 less than z, less than, let's do the other side now. Let's do the other side. So I'm going to hit the fraction button again, right? And I'm going to hit just right at the top. This is 12 minus 10.2. And we're just going to go down to where this says 1.4, right? Then you just want to hit enter right there, right? And then right after that, I got my number. So this is 1.285. So because the next number is a 5, I'm going to round the 8 up to 9, right? So this is going to become 1. Hold on 1 second. This is going to become 1.29. All right. And that's it. Questions on the calculator? Okay. All right. So yeah, you could use this if necessary. All right. Let me just switch back. A regularly scheduled program. 1 second. All right. Okay. So now, all right. Actually, just want to remind everybody about something, right? So going back to our formula sheet, this is a Z, right? So Z is a normal distribution. So we have to come down to where our normal distribution table is. All All right, this is our normal distribution table, right? Area under standard normal distribution. I just want to remind everybody about something. Let's look at this little picture right here. The table entries for Z is the area to the left of Z, right? What does that mean? That means that all these numbers that I have in here, these probabilities, these are all probabilities for Z is less than a number, not greater than. So I can't look up greater than in this table. I also can't look up in between in the table, right? So we have to do something. We have to do something about that.
The only one
Mhm.
makes sense. So, and then just taking the quarterly estimates and wire estimates. Just like.
Yes.
The way forward.
Yes. But when we find that answer is for less than. But you see, for this, we have it in between, right? So just to recap, right? Remember that whenever we have a probability that's in between, right? So one number is over here, 1.29. Another number is over here, negative 1.57. And I'm looking for this area in between, right? Hey, how are you? Good. Yes. We got to catch up sometime. Yeah. You too. Happy holidays, by the way. Yes. Every year. Yes, definitely. Definitely, I will, for sure. Actually, all right. So, hmm hmm Well, look, before we could look that up though, right? Here's what I want to do. Because I can only do less than, I want to manipulate this. So here's how I'm going to manipulate it. I'm going to show you guys, right? I'm going to take the 1.29 right here. Now, I can look up this part. I can look up all of that, everything, right? And I want to subtract this other part from it, right? I want to subtract the negative 1.57 from it, all of this part right here, right? And then that's going to leave me with the answer that I want. Essentially, looking at the formula, right? I'm trying to say I want to take the probability of Z less than 1.29 and I want to subtract the probability of the Z less than a negative 1.57, right? I'm just going to take those, I'm going to subtract those two numbers. Let's look them up, right? So first thing I'm going to look up is the 1.29, right? So I'm going to come over to my formula sheet, right? Here's my formula sheet. But you see, I have a positive 1.29, right? So I have to go to the positive table. Here's a positive table right here, right? My Z values are right here. I'm looking for 1.2. 1.2. Here it is. 1.2, right? But the 9 part that I'm looking for is actually at the top up here. So you see this is 0, 1, 2, 3, 4, 8, and then here goes the 9, right? So I'm looking for where do they intersect that, right? So this is the 0.09 and the 1.2, right? Where do they intersect that? It looks like they both intersect right here, right? So that's the 0.9015. Let's go back. Let's write that in, right? So I got a 0.9015, right? 0.9015. I want to subtract that from the other probability, which is negative 1.57, right? Let's look that up. Negative 1.57. Okay. So I'm coming back here, right? So I want to go to the negative table now, right? So negative 1.5 is coming down from here is right here. There's my negative 1.5. Now I want to look at where the 7 is, right? So I have 0, 1, 2, 3, 4, 6, and here's 7, right? So I want to know where do they intersect that, right? Negative 1.5 and a negative, excuse me, and a 0.7, right? It looks like they both intersect right here. This is the 0.0582, right? 0.0582. Let's write that in. All right. So I got 0.0582. Now, very simply, just subtract these two answers, and that's the end of the question. All right. Let's take a look. So this is going to be what? equal to 0.9015 minus 0.0582. Little subtraction, I get 0.8433. And that's it. All right. Questions on this? No? You good? All right. All right. So what does the 0.84 means? It means that a single trout taken at random is about, excuse me. Let me say it like this. Got my tongue tied a little bit. All right. So therefore, the probability, right, is about 0.8433. Excuse me. Sorry about that. Therefore, the probability is about 0.8433 that a single trout taken at random is between 8 and 12 inches long, right? Now, what is the probability that the mean length X bar of 5 trout taken at random, hold on 1 second. Read that again. What is the probability that the mean length X bar of 5 trout taken at random is between 8 and 12 inches? This is a little bit different now. This is a little bit different of a question. All right. So let me start off. They're asking you what is the probability. Oh, let me highlight where I'm getting this information from. There we go. Okay, let me bring it back. Let me bring it back. All right. So they want to know what's the probability of 8 less than or equal to X bar less than or equal to 12. Right? Right? So I'm getting the X bar from right here, right? So now it's going to be the same thing. We have an X bar distribution. We're going to change it into a Z, right? So here we go. This becomes probability of X bar minus mu over sigma over the square root of n less than or equal to Z less than or equal to X bar minus mu over sigma over the square root of n, right? Now, we're going to plug in the same numbers that we had before, right? Because we have the same mean, right? Just to recap, mu is equal to, ooh, don't tell me, 10.2. And our standard deviation is still the 1.4, right? What's up, man? Good, good? Yeah, I don't know. Huh? Yeah, I think so. I think that's what it is, right? So now what we gonna do? Just plug it in, all right? Nothing crazy here. I didn't finish grading test two, by the way. I'm gonna get that to y'all on Tuesday. All right. Yeah. Yeah. So all right, let's just plug this in. As this becomes probability of X bar is gonna be 8 minus the mean, which is still the 10.2, over our standard deviation, which is 1.4, over the square root of n, which is that we just found in this story 5. Right? So right here where it says 5 try to take in, that's my n is equal to 5. Right? All right, less than or equal to Z, less than or equal to, now this is 12 minus the mean, which is 10.2, over our standard deviation, which is 1.4, which is over our square root of 5, right? After that, plug it in the calculator, boom, 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 and then we're back to what we were just doing before, right? So let's look at how to plug this in the calculator real quick. All right, just bear with me 1 second. All right, so I want to plug this into the calculator, right? First thing, of course, you want to clear it, right? Now, if you have the 36X Pro, you're just going to hit that fraction button, which is right above the number 7 to get this little fraction thing right here going. Then you just type it in. This is going to be 8 minus the 10.2, right? No problem there. Then you're going to go down. Now, here's what I want you to do right after that. I want you to hit the fraction button again, right? So it should look something like this now, right? And then now enter in the denominator. So 1.4, then we're just going to go down, then we're going to have second square root, then hit the 5, and just hit enter. Boom. There we go. We got our number. So this is what? This is negative 3.51 less than or equal to z less than or equal to, let's do the other one, right? So again, you want to hit that fraction button, right? Then we're going to do the 12 minus 10.2. Then you want to go down and you want to hit the fraction button again, right? And then we're going to do the 1.4. Then you're going to go down and you want to do second square root and then the 5, right? After that, hit enter. Let's see what we get. So that's the 2. I'm sorry about that. So that's the 2.87. And now we're good. Just look that up, boom, 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 and we're done. All right. So let's get back to what we were doing before. All right. Here we go. So now, same story as before, though. Remember, I can't look up in between. So what am I going to do? I'm going to take the big one, which is the probability of z less than or equal to 2.87. I'm going to take that and subtract it from the little one, which is the probability of z less than negative 3.51. Okay, let's take a look at this. So 2.87, right? Hello. So for 2.87, I'm going to come over to my normal distribution table. I'm going to scroll down to 2.8. Here goes my z right here. I'm going down to where 2.8 is. Here it is, 2.8. And then I want to match that with the 7, right? So we can find the 7 at the top. So at the top, I have 0, 1, 2, 3, 4, 5, 6. Here goes 7, right? So now 2.87. Let me come down here. 2.87. Looks like it's going to meet up right here. Right? That's the 7.
Well,
Hmm?
it's a little bit more, one on now, we'll see.
Yeah. So that should be about the 0.9979, right? Let's write that in, 0.9979. All right. 0.9979, right? And then now I want to look up the negative 3.51, right? So let's take a look. Let's come back here. Now this is a negative 3.5, right? So I got to go to the negative table. So here goes my negative table, right? So I have 3.4, 3.49, no 3.5. But look right here at the bottom, right? Oh, this is what I love about having it on the computer, right? When you wear glasses, you don't gotta squint. You can just zoom it right in, right? So at the bottom in fine print, it says for values of z less than negative 3.49, use 0.00 to approximate the area. Cool, right? So given that, I know all I gotta do is plug in 0 right here, right? Little subtraction, I get the answer 0.9979, and then that's it. Questions on this? Anybody? I didn't bother to draw the distribution this time, but it's the same kind of picture as before. I'm in between the two answers. I'm going to do less than, subtract them, and that's it. All right. So we good?
So the chart basically helps us find the answer between the two, greater than less.
Well, the chart can only give me answers for less than, right? But what I can do is, because the question is asking for in between, I could find the two less than and just subtract the answers to get the answer, right? Remember, it's always the big number minus the small number, right? Probability can only be positive, it can never be negative. So that's why you always want to do the big number minus the small number. Mhm. No questions? All right, let's keep moving. Hey, all right, let's talk about the rest of this. So our number is a little bit off because we didn't round, we used the actual calculator to do our stuff, right? Which happens. Like that's a normal thing. Just make sure. Yep. Yeah, that's a normal thing that happens. Anyway, looking at the results for parts A and B, we see that the probability, right, for A was 0.8433 and the probability B was about 0.9977. They're quite different. Why is that? So according to the theorem, both X and X bar distributions have a normal distribution and both have the same mean, which is 10.2. The difference is in the standard deviations for the X and the X bar distribution. So the standard deviation for the X distribution is just sigma is equal to 1.4. But the standard deviation for the X bar distribution, right, is sigma divided by the square root of n, which is 1.4 divided by the square root of 5, which is 0.63. The standard deviation of the X bar distribution is less than half the standard deviation of the X distribution, right? So this next figure is going to show the distribution of X and X bar. So looking at this figure, right, for A and B, we see that both the curves use the same scale on the horizontal axis. The means are the same. The shaded area is above the interval from 8 to 12 on each graph. It becomes clear that the smaller standard deviation of X bar distribution has the effect of gathering together much more of the total probability into the region over its mean. Therefore, the region from 8 to 12 has a much higher probability of the X bar distribution. So let me show you guys what we're talking about here. Talking about a graph. Let me show you guys. I'm going to talk about it. 1 second. So here we go. All right. Sorry about that. Technical difficulty. Anyway, right? So the X distribution with sigma is equal to 10.2 and excuse me, X mu, I'm sorry, is equal to 10.2 and sigma is equal to 1.4 is this graph that's right here, right? You notice how it's more spread out, right? And then the area in between is 0.8433. But in the X bar distribution, where the mean for X bar is 10.2 and the standard deviation for the mean is 0.63, for samples of size n equals 5, you notice that This area is 0.9977, so this covers more of the distribution. It's more narrow, right? Okay. So theorem 7.1 describes a distribution of a particular statistic, namely the distribution of sample X bar. The standard deviation of a statistic is referred to as the standard error of that statistic, right? The standard error is the standard deviation of a sampling distribution for the X bar sampling distribution. So standard error is equal to sigma X bar, which is equal to the standard deviation sigma over the square root of n. All right, that's standard error. So the X bar distribution, given that X follows any distribution. So theorem 7.1 gives complete information about the X bar distribution, provided the original X distribution is known to be normal. What happens if we don't have information about the shape of the original X distribution? The central limit theorem tells us what is to be expected. Oh boy, here we go. We're about to get into it right now. This is that good stuff right here. All right. Again, you guys already have homework on this. It's already been posted. All right. No harm, no foul. Mhm. So we got theorem 7.2. The central limit theorem for any probability distribution. If X possesses any distribution with mean mu and standard deviation sigma, then the sample mean X bar based on a random sample of size n will have a distribution that approaches the distribution of a normal random variable with mean mu and standard deviation sigma over the square root of n as n increases without limit. So the central limit theorem is indeed surprising. It says that X can have any distribution whatsoever, but that as the sample size gets larger and larger and larger, the distribution of the X bar of the sample mean will approach a normal distribution, right? So from this relation, we begin to appreciate the scope and significance of the normal distribution, right? So for any distribution, if your sample size keeps growing, it approaches a normal distribution, right? This phenomenon. So in the central limit theorem, the degree to which the distribution of the X value fits a normal distribution depends on both the selected value of n and the original distribution of X values. Excuse me. A natural question is, how large should the sample size be if we want to apply the central limit theorem? All right. So after a great deal of theoretical as well as empirical studies, statisticians agree that if n is 30 or larger, the X bar distribution will appear to be normal and the central limit theorem will apply. However, this rule should not be applied blindly. If the X distribution is definitely not symmetric about the mean, then the X bar distribution also will display a lack of symmetry. All right. In such a case, a sample size larger than 30 may be required to get a reasonable approximation to the normal. Right. So let's talk about this for a second. If, let's say that we were a drug company and we made a new drug, right? Like let's say we invented a pill that makes people fly. Like we made a Red Bull pill. I don't know, right? Red Bull gives you wings, right? So if I test this drug on 30 people, that doesn't necessarily mean that it's good for the whole population, right? So essentially, this is what they're trying to say here, right? Theoretically speaking, if I test it on 30 people, it's good enough for the population. In practicality, that's not so, right? So when it comes to things like medicine and things like that, you want to have a sample size that's much greater. A sample size of say like 1,000 or 10,000 before you can release the drug or whatever into the population to say, okay, this drug definitively it's good and it does this. All right? That's what they're trying to say. Anyway, in practice, this is a good idea when possible to make a histogram of sample X values. If the histogram is approximately mound shaped and if it is more or less symmetric, then we may be assured that for all practical purposes, the X bar distribution will be well approximated by a normal distribution and the central limit theorem will apply when the sample size is 30 or larger. The main thing to remember is that in almost all practical applications, a sample size of 30 or more is adequate for the central limit theorem to hold. However, in a few rare applications, you may need a sample size larger than 30 to get reliable results. Okay. Good stuff, good stuff, good stuff. All right, man. I'll see you. Happy Thanksgiving, man. All right. So, what does the central limit theorem tell us, right? The central limit theorem gives us information about the characteristics of the X bar sampling distribution based on all samples of size n when n is sufficiently large, right? So for n greater than or equal to 30 in most cases, right? The central limit theorem, um, the central limit theorem tells us that the X bar distribution is approximately normal. The mean of the X bar distribution is mu. The mean of the sampling X distribution, the standard deviation, also known as the standard error, of the X bar distribution is sigma divided by the square root of n, right? So that is the standard error, where sigma is the standard deviation of the X distribution. Okay? Questions on this? Good. This little definitions is talking about it. So let's summarize this information for convenient reference. For almost all X distributions, if we use a random sample of 30 or larger, the X bar distribution will be approximately normal. The larger the sample size becomes, the closer the X bar distribution gets to normal. So furthermore, we may convert the X distribution to a standard normal distribution using the following formulas. All right. So here we go. Here's the magic right here. So using the central limit theorem to convert the X bar distribution to the standard normal distribution, the mean for X bar is equal to mu. The standard deviation for X bar is equal to standard deviation over the square root of n. Right? Our Z value is equal to X bar minus the mean mu X bar over the standard deviation sigma for X bar, which is equal to X bar minus mu over sigma over the square root of n, where n is the sample size n greater than or equal to 30. Sigma is the mean of the X distribution, and, excuse me, mu is the mean of the X distribution, and sigma is the standard deviation of the X distribution. All right? Questions on this? Once again, you don't need to remember this. It is on your formula sheet in case you want to see. Right here in chapter 7, this is where it is, right? You only need to worry about the Z formula here and the Z formula here. You should be good to go. Questions? Are we good? All right. Yes, you can use it. And you can use your two formula sheets as well. All right, this is another example. You guys can take a minute to try. I'll drink some water. Okay, Central Limit Theorem. So a certain strain of bacteria occurs in all raw milk. Let X be the bacteria count per milliliter of milk. The health department has found that if the milk is not contaminated, then the X has a distribution that is more or less mouse-shaped and symmetrical. The mean of the X distribution is mu is equal to 2,500. The standard deviation sigma is equal to 300. 1 second. In a large commercial dairy, the health inspector takes 42 random samples of milk, produce each day. At the end of the day, the bacteria count in each of the 42 samples is averaged to obtain sample mean bacteria count X bar. So assuming the milk is not contaminated, what is the distribution of the X bar? All right. So just scroll down a little bit. That should be good enough, right? So our mean mu, hold on, forgot my pen. Our mean mu is equal to the mean for the X bar distribution, which is equal to 2,500. But our standard deviation is equal to the standard deviation for the X bar distribution, which is equal to the standard deviation over the square root of n, which in our case is what? 300 over the square root of 42. Right? Let's see what that is. So I got 46.291. So that is a distribution of X bar. Any questions on this? Mhm. Real quick, just to recap, if I'm looking on my formula sheet, if I'm looking on my formula sheet, it's right here. The mean of the X bar distribution, and the standard deviation of the X bar distribution is right there. So you don't need to memorize this. It's all given to you. Okay. Now here goes a part B to this, right? It says assuming, excuse me, the milk is not contaminated, what is the probability that the average bacteria count X bar for one day is between 2,350 and 2,650 bacteria per milliliter? Okay. So here's what they're asking you. They want to know what's the probability of 2,350 less than X bar less than 2,650. All right. Let you guys try it. It's the same kind of working that we did before. After you find the answers, look it up. By the way, for test two, I still haven't finished rating it. Let you guys know I'm gonna get that back to you on Tuesday, okay? Okay. So let's convert this into a z, something that we know how to do. So this is going to become probability of x bar minus mu over sigma over the square root of n less than z less than x bar minus mu over sigma over the square root of n. Just plug in the numbers, right? Plug in the numbers. This becomes what? Probability of 2,350 minus the mean, which I forgot what that is, 2,500, 2,500 divided by the standard deviation, which in our case is what, 300 over the square root of 42, less than z, less than 2,650 minus 2,500 all over 300 over the square root of 42. All right? After you get that, plug it in the calculator, bop, 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 and then you're good to go. All right? So you already discussed how to do that in the calculator, so I'm just going to do this real quickly up here. So this is 2,350 minus 2,500 close, all right? And then 300, 42. All right, so I have the probability of negative 3.24 less than z less than, let's see what I got over here. This is 250, 2,500. 2. So now I have 3.24, right? So now same story as before. I can't look that up because it's in between, so I can only look up less than. So take the big number, leave the little number. After that, you can just look it up straight in the chart, right? So I'm looking for what? I'm looking for 3.24. I want that in the chart, right? So let's take a look. You're going to go across to your normal distribution table, but I want the positive side, right? So I'm looking for 3.2. So I'm going to go down to where the positive is. 3.2. Here it is, 3.2, right? And at the very top of the page, I'm going to look for the 4. So where's the 4? Here goes 4, right? So this is like 1, 2, 3, 4, and this is a fifth one, right? That's the 4. So looking over here, this is 1, 2, 3, 4, 5. So I have 0.994. I believe that that's where they intersect that 0.994. All right, no problem. Let's write that in. So this is 0.99, I believe it's 994. Hold on. Yep, 3 nines and a 4. Minus, now I want to look up negative 3.24, right? So I'm going to go to the negative table. Let's take a look. So I'm going to the negative table over here, looking for 3.24. Whoops. 3.24. So I'm just going to come up to where negative 3.2 is. And then go across to where the 4 is. So that's 0.0006. All right. 0.0006 for negative 3.24. So let's write that in. All right, let me just verify. 3 zeros and a 6. After that, all you have to do is subtract them and you got your answer. All right, nice and simple. So this is the 0.9994 minus 0.1236. Here's what I got, right? So I got as a final answer 0.9988. And then that's it. Questions on this? Anybody? Good? All right. So test three, I'm aiming for like the fourth, so next week, Thursday. All right. And then I'm trying to hand back test two on Tuesday. Same thing, could do test corrections, all of that good stuff, right? And then I didn't talk about this, but I'm thinking about like test four on the Tuesday after that, right? And then we just review for the final after that, and that'll be it. Yeah. No, no, no. The final. Um, give me 1 second. I'll tell you what it is right now. 1 second. I believe it's on the 18th, but I'm gonna tell you right now. I'm gonna tell you right now. Yeah, so the final is on Thursday, the 18th, right? At 2 o'clock, right? Now, normally our class is what, 2 to like 3:30, right? You guys actually get extra time on the final, right? Because it's a little bit longer. So the test is actually going to be from 2 to 3:50. All right. So just know that. Make sure you guys plan accordingly with enough time on your hands, and that's it. Tutoring will be open. I'm gonna update you guys, maybe not next week, it might be the week after, about the study halls, which will prepare you for the final. I don't have that information ready for you right now, so that's why I'm saying next week. And that'll be about it. Yeah. If it's not next week, it's the week after that I'll update you on that. But I will let you know. Yeah. Um, yep, good to go. So let's do a little interpretation. So at the end of each day, the inspector must decide to accept or reject the accumulated milk that has been held in cold storage awaiting shipment. Suppose the 42 samples taken by the inspector have a mean bacteria count X bar that is not between 2,350 and 2,650. If you were the inspector, what would your comment be on your situation, right? So for me, if it's not in that safe range, I would say that it's not safe to consume and I wouldn't consume it. That's what I would do. But let's look. Okay. So the probability that the that the sample mean X bar is between 2,350 and 2,650 for milk that is not contaminated is very high. So if the inspector finds that the average bacteria count for the 42 samples is not between 2,350 and 2,650, then it is reasonable to conclude that there is something wrong with the milk. So if X bar is less than 2,250, you might suspect someone added chemicals to the milk to artificially reduce the bacteria count. If X bar is above 2,650, you might suspect that there's some other kind of biological contamination, right? So basically, if the bacteria is not within that safe range of 2,350 to 2,650, for me, I would just say that that milk is not safe to be consumed, right? And if it's too low, there's some kind of chemicals in it. If it's too high, then there's something else wrong with it. All right. Maybe the milk got too old. I don't know. All right. So, real quick, I want to give you guys some procedure, some step-by-step procedure to help you with your homework. All right. Okay, so here's a procedure how to find probabilities regarding X bar. So given a probability distribution of X values where N is equal to a sample size and mu is the mean of the X bar of the X distribution, sigma is equal to the standard deviation of the X distribution. If the X distribution is normal, then the X bar distribution is normal. Even if the X distribution is not normal, if the sample size N is greater than or equal to 30, then by the central limit theorem, the X distribution is approximately normal. So to convert a X bar sample mean to a Z using a formula, we use Z is equal to X bar minus mu over sigma, or X bar minus mu over sigma over the square root of N, which again is on your formula sheet, so you don't need to remember it, right? Step 4, use the standard normal distribution to find the corresponding probabilities of events regarding the sample mean. All right. So let's talk about bias and variability. Whenever we use a sample statistic as an estimate of a population parameter, we need to consider both bias and variability of the statistic. All right. So a sample statistic is unbiased if the mean of its sampling distribution equals the value of the parameter being estimated. All right, let me say it again. A sample statistic is unbiased if the mean of its sampling distribution equals the value of the parameter being estimated. Okay? Good stuff, good stuff, good stuff. All right. Last little comment. Hey, the last little comment. Oh, I didn't mean to do that. All right. So the spread of the sampling distribution indicates the variability of the statistic. The spread is affected by the sampling method and the sample size. So statistics from larger random samples have spreads that are smaller. All right. So we see from the central limit theorem that the sample mean X bar is an unbiased estimator of the mean mu when N is greater than or equal to 30. The variability of the X bar decreases as the sample size increases. So in the next section, we will see that the sample proportion p hat is an unbiased estimator of the population proportion of success p rho in binomial experiments with sufficiently large numbers of trials n. Again, we will see that the variability of p hat decreases with increasing number of trials, all right? So the sample variance S squared is an unbiased estimator for the population variance sigma squared, all right? And that's about it for today. Is there any questions? Anybody? All right, in that case, happy Thanksgiving. All right. And I catch up with y'all on Tuesday. I'm gonna have the test ready for y'all. I'm gonna give that back to you. Same thing as before. You can take the test to tutoring. Any questions you got wrong, do it with the tutor, bring it back to me. I give you half of the points back that you missed. I owe you guys a class, so I'm gonna record another class. I'm gonna send that off to you guys to help you with your homework. All right. So because there's been like some new homework added, but we don't have enough information to do those last couple of questions. So I'm gonna do a really quick class and then send it off to you guys. I'm gonna try and do it tonight. If I don't get it done tonight, then definitely by tomorrow you guys will have that. You could knock that out over the weekend, and it will start fresh on Tuesday. All right. So have a great Thanksgiving. Be safe, and we'll catch up. Thanks.